You probably look at this and think it's just another old log cabin. Rough timber walls, rustic charm, maybe a quiet weekend escape for people who want to feel closer to nature. But to a group of researchers in Finland, this cabin was something else entirely. It was a problem, a contradiction, a direct challenge to everything modern engineering believes about heat and buildings. The cabin was built nearly 200 years ago, in a region where winter is not an inconvenience but a threat. Outside, the temperature was minus 30 degrees, cold severe enough to kill, cold that drains batteries, freezes engines, and shuts down the human body. Inside lived an 82-year-old woman named Helmi. There was no electricity, no modern heating system. Her fire had gone out 18 hours earlier. When researchers arrived with thermal cameras, they expected the worst. What they found instead stopped them in their tracks. They pointed the camera at the floor. 71 degrees Fahrenheit. They raised it to the ceiling. 58 degrees. The floor was 13 degrees warmer than the ceiling. That should not be possible. Every child learns the same rule in school. Heat rises. In modern homes, warm air collects at the ceiling while cold settles near the floor. But in this cabin, the rule was reversed. Helmi walked barefoot across warm floors. She slept comfortably. She woke up rested. Next door stood a modern house, built in 1985, with better insulation, electric heating running all night, and all the advantages of modern engineering. Same weather, same cold. The thermal camera showed a hot ceiling and a cold floor. The homeowner shivered under blankets. The heating bill that month was $340. 2 houses. Same winter. One consumed energy constantly and still felt cold. The other consumed nothing and felt warm. From the perspective of a historian of medieval and pre-industrial technology, this is not nostalgia and it is not romantic storytelling. It is evidence. Evidence that older builders did not merely endure winter, they understood it. This cabin is not warm because of advanced materials. Its walls are thinner than many modern homes. It is not warm because of insulation as we define it today. It is warm because it was designed around human biology, thermal physics, and energy scarcity. Principles refined through centuries of observation, trial, and survival. What modern construction treats as separate problems, heating, comfort, airflow, efficiency, medieval builders treated as one integrated system. A system with a single purpose: keep people alive when energy is limited, winter is brutal, and failure means death. This cabin does not depend on constant power. It does not collapse when the grid fails. It captures heat, stores heat, protects heat, and delivers it where the human body needs it most. And it does this through 6 interconnected systems that modern construction has almost completely forgotten. Before we examine those systems one by one, ask yourself a simple question. If the power went out tonight, in the middle of winter, how long would your home remain safe to live in? The answer to that question is why this 200-year-old cabin still matters today. When we talk about heating a home, most people imagine flames and warmth as the same thing. If the fire is big, the room should be warm. That assumption feels logical, but medieval builders knew it was dangerously wrong. To understand why, watch a modern fireplace for a moment. Light the fire, stand back, and you feel heat only when you are directly in front of the flames. Now, step outside while that fire is burning and place your hand near the chimney. It is hot, sometimes too hot to touch. That heat is not warming your home. It is escaping straight into the sky. In fact, a roaring modern fireplace often makes a room colder. As hot smoke rushes upward, it pulls warm air from the room with it, creating negative pressure. Cold air is drawn in through every crack and seam. The fire looks powerful. but it is quietly draining heat faster than it creates it. Medieval builders learned this lesson the hard way because they could not afford to waste a single piece of firewood. Now, travel back to rural Russia in the 17th century. Winter lasts 7 months. Wood is life. If you burn too much, you freeze later. Russian builders developed a radically different solution. They built what we now call masonry heaters. Massive brick structures, sometimes 8 feet tall, constructed inside the living space itself. The design defies modern intuition. Smoke does not go straight up. When the fire is lit, hot smoke rises into a chamber, hits a wall, and is forced sideways through a long brick channel. Then it turns downward, then sideways again, then up slightly, then sideways again. Before the smoke ever reaches the chimney, it travels through roughly 32 feet of winding masonry channels. As that smoke crawls through the maze, every inch of brick absorbs heat. The smoke enters at temperatures around 1400 degrees Fahrenheit and exits barely warmer than room temperature. Nearly all of the thermal energy has been stripped away and stored in thousands of pounds of brick and stone. Touch the chimney outside while the fire burns, and it is barely warm. The heat never escaped. It stayed inside the house. That stored heat then radiates slowly and safely for the next 24 hours. Surface temperatures stay between 100 and 130 degrees, warm to the touch, never dangerous. One short fire in the morning heats the home until the next day. This was not accidental. Over 4 centuries of trial and error, builders discovered something modern engineers often overlook. Timing matters. If smoke moves too fast, it escapes before transferring heat. If it moves too slowly, it cools too much, condenses, creates tar, and blocks the system. 32 feet of channel creates roughly 9 seconds of contact between hot gas and cool masonry, the precise window where maximum heat transfer occurs. They had no thermometers, no equations, only observation passed from one generation to the next. Now, compare that with what happened during the American energy crisis of the 1970s. Fuel prices spiked. Engineers were called in to improve fireplaces. They focused on one goal: get smoke out faster, cleaner burn, less smoke indoors. And they succeeded. Modern fireplaces move smoke incredibly efficiently, but faster smoke means less heat captured and more heat wasted. A traditional masonry heater captures roughly 80% of a fire's energy. Even the best modern high-efficiency fireplaces struggle to reach 60%. We made fireplaces better at removing smoke and worse at keeping people warm. Finnish researchers confirmed this in 2019 when they tested preserved masonry heaters built before 1850. Every single one outperformed modern EPA-certified wood stoves by large margins. Not because of technology, but because of physics understood long before modern engineering. Medieval builders were not heating air, they were charging a thermal battery. And that difference is the foundation of everything that follows. Capturing heat means nothing if that heat never reaches the human body in the right way. Medieval builders understood something modern construction still struggles with. Comfort is not controlled by air temperature alone. It begins at your feet. Stand barefoot on a modern floor in winter and count to 10. Your toes tense. Your feet go numb. Instinctively, your body reacts. That reaction is not psychological, it is biological. The soles of your feet contain more than 70,000 nerve endings, dense sensors that constantly report environmental safety to your brain. When those sensors detect cold, blood vessels constrict automatically. Your brain receives a simple message: danger, cold environment. Even if the thermostat reads 70 degrees, your body does not feel warm. Modern research confirmed this in 2008 when medical studies showed that once foot temperature drops below 68 degrees Fahrenheit, the body's thermoregulation system triggers a full cold response. Medieval Scandinavian builders did not need medical journals to know this. They learned it through lived experience. Warm feet meant a warm body. Warm air above the head meant almost nothing. So, instead of heating ceilings, they heated the ground beneath their homes. The brilliance of the medieval floor is easy to miss because you never see it. The finished floorboards look ordinary. The intelligence is hidden below. The first layer consists of rough logs, 8 inches in diameter, laid across stone piers. These logs were never meant to be seen or finished. They exist only to carry mass. Above them sits a second layer, 12 inches of densely packed material, a mixture of sand, clay, and often wood ash from previous fires. This layer alone weighs roughly 180 pounds per square foot. In an average room, that mass adds up to nearly 14 tons beneath your feet. On top of that rests the walking surface, thick hardwood planks fitted tightly together. The total floor thickness reaches nearly 22 inches. Now, place the masonry heater directly on this floor, not raised, not isolated, but sitting directly on top of it. When the fire burns, heat radiates in every direction, not just upward, but sideways and downward, sinking into those tons of sand and clay like charging a battery. When the fire goes out, the floor remembers. For the next 18 hours, stored heat rises gently from below. The surface temperature stays near 70 degrees, similar to sun-warmed stone. A Norwegian family measured this throughout an entire winter in a restored 18th century cabin. Each morning, they burned one fire for about 2 hours. Outside, temperatures dropped to -20, yet the floor remained above 68 degrees until 11 at night, every single day. The air temperature could fall to 60 degrees and the house still felt comfortable because the body felt warm from the ground up. Modern, radiant floor heating tries to imitate this sensation using hot water tubes beneath the floor. It feels good while it runs, but there is a critical difference. Those systems have almost no thermal mass. The moment the pump shuts off, the floor cools within hours. Energy must be supplied continuously. Medieval floors required no continuous input. They radiated stored warmth long after the fire died. Modern building codes measure insulation values, how slowly heat moves through materials. They almost completely ignore thermal capacity, how much heat materials can actually store. A medieval floor with low insulation but massive storage outperforms a modern floor with high insulation and no memory. The codes measure the wrong thing. By warming the feet, medieval builders warmed the entire body, using less fuel and less effort. But even a warm floor cannot protect heat if it escapes every time a door opens. And that problem leads directly to the next system. Even the best heat capture and the warmest floors mean nothing if cold air is allowed to invade the house unchecked. Medieval builders understood something modern homes repeatedly ignore. Most heat loss does not happen slowly through walls. It happens instantly through openings. Open a modern front door in winter for just 5 seconds and feel what happens next. Cold air does not politely mix with warm air. It pours in at floor level like an invisible river, spreads across the room, and settles. Your heating system immediately goes to work trying to fight it. Every door opening becomes a direct energy loss. Medieval builders never allowed this. Instead, they created what can only be described as a winter trap. Travel to northern Sweden and step inside a surviving cabin built in the late 17th century, still occupied today. The entry feels strange to modern eyes. There are 2 doors, not one, with a small unheated space between them. Locals call it the vintering, the winter catch. The sequence is deliberate. You stand outside in -20-degree air and open the first door. You step into a tiny chamber, barely large enough for one person. You close the door behind you. Only then can you open the second door and enter the warm living space. At no point does outside air rush directly into the home. The cold you bring with you stays trapped in that small buffer room. Over the next few minutes, that space slowly warms to around 40 degrees, not from a heater, but from a small controlled bleed of heat through the inner door. Instead of forcing the house to absorb a shock from -20 to 70 degrees, medieval builders created a thermal staircase, cold to cool, cool to warm, never cold to warm all at once. This principle alone saves enormous amounts of energy. A Minnesota family tested it by building 2 identical cabins, same size, same insulation, same thermostat settings. One had a single door. The other used a true double-door airlock. Over one winter, the single-door cabin spent $920 on heating. The airlock cabin spent $640. $280 saved by geometry alone. There is another detail most people miss. The doors open in specific directions. The outer door opens outward, away from the house. When winter wind presses against it, the pressure seals the door tighter. Warm air inside expands slightly when a fire burns, creating gentle, positive pressure that also pushes the outer door closed. The system naturally wants to stay sealed. The inner door opens inward, into the warm space, where pressure differences are minimal. Modern mudrooms fail because they are heated. They are just another interior room with a door to outside. No buffer, no stepping, no protection. A true airlock must be unheated. That is the entire point. Arctic research stations still use this principle today, not because it is old, but because it works. During the Texas freeze of 2021, millions of homes lost power. Cold air leaked continuously through modern doors. Indoor temperatures dropped to freezing within hours. Families shoved towels and blankets under door gaps, trying desperately to recreate what medieval builders had solved permanently centuries earlier. The winter trap was not a luxury, it was survival logic. But even a sealed entry and warm floors cannot fully stabilize a home if the walls themselves behave like thin shells instead of reservoirs. And that brings us to the next system, where medieval builders turned walls into thermal memory. Even with heat carefully captured, stored in the floor, and protected at the doors, a house can still fail if its walls work against it. This is where medieval builders revealed one of their most powerful insights. Walls are not just barriers, they are batteries. Spend a winter night in a modern home during a cold snap. Outside temperature drops from 20 degrees at sunset to -10 by midnight. Inside, the furnace cycles on and off, overcorrecting, undershooting, constantly chasing comfort. You wake up at 3 in the morning either too hot or too cold. The temperature swings never stop. Now, spend that same night in a cabin with 10-inch thick log walls. Outside conditions are identical. Inside, the temperature barely moves. It stays calm, stable, predictable. Touch a modern wall and it feels thin, hollow. Knock on it and you hear empty space behind drywall, insulation, and air. Touch a log wall and you feel solid mass. Knock on it and the sound is dull, dense, heavy. That mass changes everything. During the day, when sunlight strikes the exterior of a thick wooden wall, the heat does not rush inside. The wood absorbs it slowly, storing energy deep within its fibers. When night falls and the outside temperature drops sharply, the wall does not immediately become cold. It releases that stored heat back into the interior, gradually, evenly, hour after hour. The wall acts like a thermal shock absorber, smoothing out extreme temperature swings before they ever reach the living space. Engineers call this effect a thermal flywheel, the same principle used in heavy rotating machinery to keep motion stable even when power input fluctuates. Medieval builders achieved the same result with nothing but wood, thickness, and time. Swedish researchers tested this in 2017 by building two identical small structures. One used modern framing and drywall, the other used solid 10-inch log walls. Over 2 weeks in February, outside temperatures swung wildly, sometimes 40 degrees between day and night. Inside the modern structure, temperature varied by 15 degrees even with heating running constantly. Inside the log structure, the temperature fluctuated by just 3 degrees total. The walls were doing the work. A typical medieval cabin contains nearly 60 tons of solid wood. That is an enormous amount of thermal storage surrounding the living space on all sides. A modern home may contain only a few hundred pounds of drywall and framing lumber in its walls, almost no storage at all. During a 3-day cold snap in Norway, researchers monitored both types of homes. The modern house required its heating system to run nearly 18 hours per day to maintain comfort. The medieval cabin needed a single fire lasting 2 hours per day. The walls absorbed heat during the burn and released it steadily for the remaining 22 hours. A National Bureau of Standards study from 1980 confirmed this behavior. 2 structures were built, one with 7-inch log walls, the other with conventional framing and higher insulation values. During deep winter, energy use was similar, but during spring, when temperatures fluctuated daily, the log building used 46% less energy. Thermal mass becomes more valuable as variability increases. Modern building codes focus almost entirely on resistance, how well materials block heat flow. They largely ignore capacity, how much heat materials can actually hold. Medieval builders optimized for stability, not just efficiency, and thick walls did more than stabilize temperature. They quietly transformed the air itself, creating an indoor environment modern homes struggle to reproduce. The thick walls of a medieval cabin did something else that modern homes rarely achieve. Something you can feel immediately, but almost never measure until it is gone. They regulated the air itself. Walk into a modern house in the middle of winter. The heat is running, the windows are sealed tight, and after a few minutes your throat feels dry. Your nose stings. Your lips crack. Static electricity snaps every time you touch metal. Check a humidity gauge and the reading often sits around 20 to 25%, drier than many deserts. This is the modern winter experience. We respond by adding machines. Humidifiers run constantly. Filters clog. Maintenance never ends. Now, walk into a log cabin during the same winter conditions. The fire may have gone out hours earlier. The air feels different immediately. It feels softer, heavier, easier to breathe. Your throat does not dry out. Your sinuses relax. Humidity naturally stays in the comfortable range between 40 and 50%, without a single machine running. Medieval builders did not talk about indoor air quality, but they understood materials. Solid wood walls do not behave like drywall and plastic barriers. Wood is hygroscopic. It absorbs moisture from the air when humidity rises and releases it back when humidity drops. Every time people cook, breathe, bathe, or boil water, moisture enters the air. In modern homes, that moisture has nowhere to go. It condenses on cold surfaces or forces ventilation systems to remove it, drying the air even further. Plastic vapor barriers protect wall cavities, but they also prevent the living space from regulating itself. Medieval walls solved this problem passively. When humidity rises above comfortable levels, the wood absorbs water vapor into its fibers. When the air becomes too dry, the wood releases moisture slowly, stabilizing the environment without energy input. A family in Vermont restored an old log cabin and monitored humidity for an entire year. In winter, levels stayed between 42 and 48% without a humidifier. In summer, levels stayed below 55% without a dehumidifier. Their modern house next door required both machines to maintain comfort. Research confirmed this effect. Studies showed that an 800-square-foot cabin with exposed wood surfaces can absorb and release more than 18 pounds of water naturally, acting as a massive moisture buffer. But the walls did not stop there. They also improved air quality. Modern furniture, carpets, paints, and adhesives release volatile organic compounds into indoor air. These chemicals linger in sealed environments, contributing to headaches, irritation, and long-term health issues. Drywall and synthetic materials do nothing to remove them. Wood does. The fibers within solid timber actively absorb certain volatile compounds, pulling them out of the air. Finnish researchers compared indoor air in modern homes and log cabins furnished with identical materials. The cabins showed 20 to 30% lower concentrations of airborne chemicals. People often say old cabins smell better or feel healthier. That sensation is not nostalgia, it is measurable chemistry. Medieval builders did not design healthier homes by accident. They built with materials that worked with human biology instead of fighting it. Thick walls stabilized temperature, moderated humidity, and quietly cleaned the air, all without consuming energy. And yet, even with perfect walls, warm floors, captured heat, and sealed entrances, one final mistake could waste a quarter of all remaining warmth. That mistake comes down to geometry. There is one final principle so simple that once you see it, it becomes impossible to ignore. Yet modern construction abandoned it almost completely. Geometry. Look at a typical modern living room with a fireplace. Where is it placed? Against an exterior wall, centered for visual impact, with a large chimney proudly visible from the street. It looks impressive. It also wastes heat. Stand next to that fireplace and place your hand near the back where it meets the outside wall. It is warm. Very warm. That warmth is not helping you. It is bleeding straight through the wall and into the cold outdoors. A fireplace has 4 sides. In a modern layout, 3 sides face the interior, while one faces an exterior wall. Roughly 1/4 of the heat is lost immediately. Medieval builders never made this mistake. In surviving structures across Scandinavia and Eastern Europe, the primary heat source is always placed in an interior corner, never against an outside wall. Every side faces living space. Every surface radiates useful heat. Nothing is wasted. This was not coincidence. A Swedish architect surveyed 40 preserved medieval buildings and found 0 exceptions. The heat source was always located at an interior corner. Corners matter for another reason as well. They are naturally the coldest points in any structure. 2 exterior surfaces meet, allowing heat to escape faster. In modern homes, corners often develop condensation, dampness, and mold. By placing the warmest object in the coldest location, medieval builders eliminated the problem entirely. The corner became the warmest part of the room. Condensation could not form. Mold had no chance to grow. This final insight ties the entire system together. The masonry heater captures heat instead of wasting it. The massive floor stores heat and delivers it where the body senses warmth first. The airlock prevents cold from ever entering the living space. Thick walls act as thermal flywheels, stabilizing temperature swings. Wood surfaces regulate humidity and improve air quality. And the placement of the heat source ensures every unit of energy works for the people inside, not the environment outside. None of these systems work well alone. Together, they form a house that survives when conditions are brutal, energy is scarce, and failure is not an option. These were not primitive solutions. They were refined through centuries of observation, trial, and survival. Homes that kept families alive through winters that killed others. Homes that improved with age instead of degrading. We abandoned these principles in exchange for speed, convenience, and cheap construction. We traded resilience for dependence. The result is housing that functions only when the grid functions. Homes that become unlivable within hours of power loss. Homes that cost less to build, but far more to operate over time. That 200-year-old cabin, still standing in the cold, is not a relic. It is proof. Proof that comfort does not require constant energy, that efficiency is not the same as resilience, and that working with physics will always outperform fighting it. This is not about returning to the past. It is about remembering principles that work, principles we forgot, and principles we urgently need again.